In this section, we're going to look about Taylor polynomials and approximations using these Taylor polynomials. So we've looked at different characteristics of functions now that can be described by different levels of the derivative. The first derivative tells you about the slope, the second derivative tells you about the concavity, and so on. And so we've also seen that when it comes to derivatives, polynomials are obviously the easiest functions to work with. And so Taylor and McLaurin, two mathematicians who are credited with working on these things, they found a way that we can use polynomials to approximate other elementary functions, the ones that are less friendly, like sine, e to the x, those sorts of things. So to find a polynomial p that approximates another function f, we first need to choose a number in the domain of f at which f and p have the same value. So we want the value of the function to be the same. The polynomial that we're going to create has to equal the value of whatever f is that we're trying to approximate. When you choose that point, then the polynomial we're created, we say it's either expanded about C or centered at C. So if we think about visually what that means, if you look at the graph over here, if we think about this line here as the polynomial P and this curve as the function f, we need to make sure that this point right here is the same. This point of intersection between the two is the same, okay? Now, our goal is to find a polynomial whose graph resembles the graph of f near this point. Here's what's interesting about these. It's not going to match everywhere, and you may need to use a different polynomial to approximate different areas of the function, but close to this point, it's going to be a pretty decent approximation. We've seen this already when we used tangent lines to approximate the value of a function. We said that was called local linearization. We talked about the idea of how, again, if we think about this tangent line here on this graph, very, very close to C, this is a decent approximation. But if I move out here, we're getting much further from where the graph actually is, so it's not as good of an approximation. Well, what if we could create a polynomial that was a little bit better approximation? Instead of looking at a line, maybe I want to pick something that's more curved. Maybe instead of something that's curved like a parabola, I want to do something that moves around a little bit more like a cubic. And so we can do a linear approximation by making sure that both the value of the function is the same and the value of the slope is the same. That's the first thing that we're going to look at. In this example, we want to take the function f of x equals e to the x and find a first-degree polynomial function, p1 of x. We're calling it p1 because we're making a first-degree polynomial. We want it in the form of a sub 0 plus a sub 1 x, whose value and slope agree with the value and slope of f at x equals 0. So the first thing that we need based on these requirements is we need for f of 0 to equal p1 of 0. We said the value of the function needs to be the same as the value of the polynomial we're creating. So how would we do that? Well, let's first figure out what f of 0 is. F of 0 is going to be e to the 0, which is equal to 1. That means then that we need p1 of 0. We know that we're going to start with a sub 0 plus a sub 1 times x, and we know that x is 0. Okay, we don't know what the a's are yet. That's kind of the point. Well, this is going to be 0, so I know that whatever p1 of 0 is, that's what I need a sub 0 to equal, and so we're going to let a sub 0 equal 1. That's how we're going to get f of 0 and the value of p1 of 0 to be the same, okay? Now, the second thing that we need is we need for their slope to match. So that means that we need f prime of 0 to also equal p prime of 0, p1 prime in this case. So the way we're going to do that, let's think about, we know what f is, so let's look at f prime of 0. Well, the derivative of e to the x is still going to be e to the x, so this is going to be e to the 0, which is also 1. And now we know if we take the derivative p1 prime of x, no matter what x is, remember a sub 0 is a constant, and then we have a sub 1x, so the derivative is just going to be a sub 1. That tells us that we need to let a sub 1 equal 1 as well, because again, we want 1 and a sub 1 to be the same. So now that tells us that the polynomial that we want, p sub 1 of x, this is the first degree polynomial that's going to approximate f of x equals e to the x for values near x equals 0, is going to be 1 plus x. 1 is a sub 0, and a sub 1 is also 1 when we plug that in. So that is called the first degree Taylor polynomial centered at 0. That's what we just found. And so for values very, very close to 0, 1 plus x is going to approximate the value of e to the x pretty well. That's what we have just found, okay? So let's formalize this a little bit. This one, we only looked at the function value and the slope, but now we could add more characteristics here. Let's say that I want the function value to be the same, the slope to be the same, and I want the concavity to be the same. If we curve that polynomial the same way that the function curves, that's going to be an even better approximation, and we might be able to take our interval a little bit wider. We can get a little bit further from 0, and it would still be a good approximation. So here's the information about Taylor and Maclaurin polynomials. Okay, so it's two different mathematicians. They were kind of working on this parallel to each other at the same time. So they both get a little bit of credit here, but they are a little bit different. So the polynomial approximation of f of x equals e to the x that we just did was expanded about c equal to 0. But for any arbitrary value of c, we would have a polynomial in this sort of form. Ours was c equals 0, so you can just ignore that term. We have a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, and so on, however many degrees you want to go. So when you do repeated differentiation here, if you kind of look at the pattern of what is happening, you can see every time that constant is going to be dropping out, and because of the way you take the derivative with polynomials, if we look at, say, this term here, the a third term, the first time we take the derivative, we are going to do 2 times 3 right here, times a3 times x minus c to the first. Then the next time we multiply, it's going to be 1 times 2 times 3 times a3, and so on. If you expand that out for broader, if you had something like to the 6th power, you'd multiply by 6, and then you'd have the 5th power, then you'd multiply 5 times 6, and you'd have the 4th power, 4 times 5 times 6, and then the 3rd power. So what we can see is actually happening here is you're multiplying by successive values all the way down to 1, and we know that the way we can represent that mathematically is with this, whoops, that's underneath my writing, this factorial notation. Okay, so what we see, remember, n factorial is n times n minus 1 times n minus 2 times n minus 3, and on down to 1. Like I was showing, 6 times 5 times 4 times 3 times 2 times 1 would be 6 factorial. So that's why a factorial sneaks its way into this. The value, then, if you think about the process we did to get A1 and A2, if we were to continue that process generally, we can find that the following is true. f of c is always going to be the value of a sub 0. F prime at c is going to be the value of a sub 1. F double prime at c divided by 2 factorial gives us the value of a sub 2, and on and on and on. These coefficients allow us to obtain the definition of Taylor polynomials. This is named after Brooke Taylor, and Maclaurin polynomials, which is named after Colin Maclaurin. This sounds like a lot. It's a lot easier to do than you think. Notice the patterns here. So here's the two definitions. A Taylor polynomial can be centered anywhere. So C can be 2, 5, negative 19, whatever we want. If we choose to center it at 0, then it's still a Taylor polynomial, but that is specifically a Maclaurin polynomial. Maclaurin was focused on centering at a value of 0. So anytime it says find the Maclaurin polynomial, they're not going to give you a center because it's implied that the center is 0. Every single derivative, these all match in kind of a triangle, okay? Look at what happens here. This is essentially the 0 derivative, we don't really call that a thing, but this is how you can think of it, times x to the 0 over 0 factorial. 0 factorial is equal to 1. That's a definition. So you just end up with x with f of c on its own. This is the first derivative, first power over 1 factorial, which is just 1. So we don't write these things out. But then the next term is second derivative, second power 2 factorial. The next one would be f triple prime of c times x minus c to the third over 3 factorial. It all goes together, 3, 3, 3. And so in general, you want the nth derivative. Your coefficient will have the nth power, and you divide by n factorial. That's how you're going to figure these out, okay? So we can find the general nth polynomial then by using this process and noticing the patterns. So we want to go ahead and get a few of the first terms here. So for this first example, I'm going to get you started. I want you to find the nth Maclaurin polynomial for f of x equals e to the x. Now, we already kind of started this one in the first example. Maclaurin, remember, means that c is equal to 0. That's the implication right there. And then we need to go ahead and figure out some of the values of f of c, f prime of c, f double prime of c, and so on. So we know that f of 0 is going to be e to the 0 power, so that is 1. F prime of 0 is also going to be e to the 0 power equals 1. F double prime of 0, also going to be e to the 0. Because remember, when we keep taking the derivative of e to the x, it's always going to stay e to the x. So every single time, these are all going to be equal to 1. So here is how this is going to set up. In general here, the nth polynomial at x for this approximation is going to start with f of 0 plus f prime of 0 x plus, again, 2, 2, 2. So it's going to be f double prime of 0 x squared over 2 factorial. The next one would be 3, 3, 3, f triple prime of 0 x cubed over 3 factorial. Plus, this is going to go on forever because we want it out to the nth. But the last one is going to be the nth derivative, at 0. Oh, no, I did want that. Times x to the n over n factorial. I don't know why this is writing funny today. Okay, and so that is the general pattern, but we know what all of those f of 0, f prime of 0, and so on values are, so we can go ahead and substitute this in now. So we have p sub n of x is going to be 1 plus 1x plus 1 over 2 factorial. 2 times 1 is 2, x squared, plus 1 times x cubed over 3 factorial, 3 times 2 times 1. This is going to be 1 over 6 x cubed plus ... We know the pattern of these derivatives. We can also make the assumption that the nth derivative at 0 is still going to be 1, no matter what happens here. And so we're going to have 1 times x to the n over n factorial. That's our nth term. And so we now have this built where I could say, find me the 5th degree Taylor polynomial, and I just follow this pattern till I get the 5th, and I would be done there. But this is the nth in general, okay? The last one that I want to look at here is one that is not centered at 0 and what that would look like. So this is asking us for 5 different polynomials. We want P0, P1, P2, P3, P4. And we want to use that to approximate the natural log of x centered at c equals 1, okay? So all of our derivatives, we want to know the value at x equals 1. So I need to go all the way out to the 4th derivative to be able to get my 4th Taylor polynomial. And you can work this on your own, but to save us some time, I'm going to go ahead and show you what those derivatives come out to be. So these are all of our derivatives. Now to figure out what our coefficients are, we need to evaluate all of these at c equals 1. That's what we want to plug in for x in all of these cases. So this is the x value that we want to plug in for all of these functions. We want f of c, f prime of c, and so on. And here's what we get. Once we have those values, now we're going to build our polynomials exactly the same way. So we'll start one at a time. So P0 of x. Remember, the first term is always just your first number, so that's going to be 0. Done. P1 of x is going to be 0 plus the first term is x minus 1 to the first power over first factorial, so that's all we get. The second one, P2 of x, is going to be x minus 1, that's what we started with, plus the coefficient of the next one has to be negative 1. So really, instead of a plus, we want a minus here, x minus 1 to the second over 2 factorial. P3 is going to be everything we already had, x minus 1 minus x minus 1 squared over 2 factorial. This one's going to have a coefficient of plus 2 x minus 1 cubed over 3 factorial. And then you could do the same thing with the 4th. I'm going to leave you to finish the 4th degree polynomial on your own. And I'm going to leave you to look at example 4 in the notes on the PDF that is posted. But this is hopefully enough to get you started.